There's a comet passing Earth tonight that doesn't behave like a comet. Let me rephrase that. We're calling it a comet because that's the closest box we have to put it in. The box is splitting at the seams. Oumuamua back in 2017 was a strange guest, a tumbling interstellar rock that defied easy categorization. It made us uncomfortable. It pushed the boundaries of what we thought we knew about natural objects. But what's happening tonight, with this object we're tracking as 3I Atlas, is different. This isn't just pushing boundaries. This looks like someone took the rulebook, studied it carefully, and is now executing a maneuver that technically fits on the page, while violating every single principle the words were meant to uphold. This isn't an anomaly, it's a performance. And the performance has a chilling, precise logic to it. 3I Atlas isn't tumbling. It's maintaining perfect sunlock orientation, its face steadily aimed at the sun, while bending around gravitational fields in ways that suggest navigation, not drift. The chemistry is wrong. The trajectories are too clean. The timing is too convenient. Analysis from teams like Dr. Amir Siraj and Dr. Avi Loeb reveals geometric relationships that natural chaos doesn't produce. It's the difference between finding a curiously shaped stone on a beach and finding a stone shaped like a precise interlocking gear. One is a quirk of nature. The other implies a function, a place in a larger machine we can't see. And suddenly, we're faced with an uncomfortable possibility that is shifting from the fringe into sober scientific discussion. What if this isn't a rock? What if it's not even a comet? What if what we're calling 3I Atlas is a reconnaissance probe, a technological scan of our system disguised as a piece of cosmic debris? Tonight, we're going to walk through the evidence that has brought us to this point. We'll break down the Trojan Horse hypothesis, the industrial chemistry anomalies, the beam of material that shouldn't be able to exist, and the trajectory that reads less like an orbit and more like a flight plan. By the end, you'll see why this might be the moment everything changed. And we're only just beginning to notice. If these anomalies have you questioning what we're actually witnessing tonight, I need your support to grow this channel. So, make sure you like this video and subscribe this channel. Follow the analysis. We're going to be tracking this in real time. And I want you to comment below. Tell me where you're watching from, what time the closest approach happens in your time zone, and give me your honest gut assessment. Do you think we're watching a natural object behaving strangely, or something else entirely? This is a live conversation. Let's have it. Tonight is the event. You're reading this at a very specific moment in time, not because you stumbled upon it by chance, but because tonight, right now, something is happening above your head that might never happen again in human history. The object we're calling 3I Atlas is making its closest approach to Earth. And if the data is even partially correct, we're not just watching a flyby, we are participating in a test. Let me be absolutely clear about what closest approach usually means in astronomy. Most of the time, when scientists talk about objects passing near Earth, they're describing a mathematical moment, a point on a graph where two trajectories intersect at their minimum separation. It's a geometry problem, clinical and predictable. We calculate it, we observe it, we file it away. The object was never visiting us any more than two strangers passing on opposite sides of a highway are visiting each other. It's just math in motion, and the universe is full of it. But 3I Atlas isn't being framed that way anymore. Something has fundamentally shifted in the language around this object over the past few weeks. Scientists who initially called it unusual or interesting started using words like coherent and systematic. Dr. Avi Loeb, who has made a career of saying the quiet parts out loud about Oumuamua and now this, published an analysis that reads less like a dry research paper and more like someone trying very carefully and very urgently to tell you that your house might be on fire. He's not yelling, he's just pointing at the smoke, asking if you smell it too, and handing you a fire extinguisher just in case. His tone is what's so arresting. It's the calm, precise voice of someone who has run out of ordinary explanations. Here's what makes tonight different. This isn't about distance. It's about timing, geometry, and something far more unsettling, the possibility that we are watching a black swan event as it actually happens. You know what a black swan is, right? Philosopher and statistician Nassim Nicholas Taleb defined it as an event that is extraordinarily rare, has an extreme impact, and is only obvious in hindsight. The important part is that third, characteristic. Black swans don't announce themselves. They look like background noise until suddenly they're the only signal that ever mattered. September 11th was a black swan. The 2008 financial crisis was a black swan. They are the moments where everyone afterward says, "How did we not see this coming?" Even though all the pieces were visible the entire time. Loeb's argument is that 3i Atlas might be the first black swan we can actually see forming. Not after it happens, not when historians piece it together decades later. Right now, tonight. And that should make you deeply uncomfortable, because it means we are living in the before time of a potential paradigm shift. And before times are always filled with people confidently explaining why the thing that's about to happen can't possibly happen. Let me address the fear part first, because I know that's sitting in your mind. There is no confirmed threat here. No one is predicting an impact, an attack, or any kind of immediate disaster scenario. That's not what this is about. This is about significance, not danger. Those are very different things. You can have a historically transformative event that doesn't involve anything dramatic happening at all. Sometimes the most important moments are the ones where we simply realize something we didn't know before. Columbus landing in the Americas didn't require explosions for it to change the world. It just required recognition. What changed in the scientific conversation around 3i Atlas is the pattern recognition. Early observations noted anomalies, odd behaviours that didn't quite fit. Then more data came in, and those anomalies started correlating with each other. Then the correlation started suggesting a system, a logic, an underlying architecture that purely natural explanations struggle to account for without performing intellectual gymnastics. Loeb's rhetorical progression mirrors this exactly. He started with, "Here's something strange." Then he moved to, "Here are multiple strange things that might be connected." Now he's at, "Here's what it looks like when you treat them as a unified phenomenon." That shift is everything. It's the difference between saying, "This rock is oddly shaped," and saying, "This rock is shaped like a key and we're standing in front of a door." Neither statement proves anything, but they orient your attention in radically different directions. There's another element to tonight that nobody in the mainstream wants to say out loud, but I'm going to say it. If this object is technological, if it has been under any form of guidance, or is performing any form of active manoeuvring, then it knows we're here. It has been on a trajectory that brings it through our neighbourhood at a moment when we have telescopes powerful enough to see it. That's not necessarily a threat. That's observation. And if we're observing it while it's observing us, then what's happening tonight isn't a flyby. It's a mutual assessment. Two intelligences sizing each other up from a distance, neither making sudden moves, both trying to understand what they're looking at. You don't have to believe that for this to be important. You just have to acknowledge that the possibility exists, and that dismissing it too quickly might be a mistake we can't undo. Here's the thing that makes black swans so psychologically difficult. Nothing dramatic has to happen for this to be historic. If 3i Atlas passes by, continues on its way, and we're left with a data set that stubbornly refuses to resolve into comfortable natural explanations, that might be enough. The event isn't the passage itself. The event is the moment we stop being able to comfortably categorize what we're looking at. That moment might have already happened weeks ago, and we're just waiting for the scientific and public consensus to catch up. Loeb knows this. His writing lately has this preemptive quality to it, like he's trying to get ideas on the record before the post-flyby narratives have a chance to sanitize them. Once the object is past us, once the immediate observation window closes, there will be enormous institutional and psychological pressure to file this under interesting anomaly, probably natural further study needed. The comfort of that phrasing will be irresistible. But right now, before that window closes, while the data is still streaming in and the geometry is still active, we have a rare chance to ask the uncomfortable questions without the benefit of hindsight. We can look at the raw puzzle before the picture on the box tells us what it's supposed to be. So, let's ask, what if the real signal isn't the motion at all? What if it's the geometry? What if the way this object moved through space matters more than where it's going? That question leads us into the next layer, into the numbers that start to tell a story intuition alone can't explain. It leads us to the first major anomaly that made everyone sit up straight. The 16-degree problem. Gravity bends everything. That's not a metaphor, it's the foundational physics of our universe. When an object falls toward the sun, its trajectory curves, accelerates, and then curves again as it slingshots back out into the black. This is called perihelion gravitational deflection. It happens to every comet, every asteroid, every speck of dust that ventures too close to a massive body. The amount of that bend depends on velocity, mass, and proximity. We've been calculating these arcs for centuries. Our models are exquisite, honed by observations of countless objects. They are the bedrock of orbital mechanics. So, when an object behaves in a way that respects the letter of this law but seems to dance along its edge, that's when physicists get a specific cold feeling in their stomachs. 3I Atlas, during its own plunge around the Sun, underwent a reported 16.4-degree trajectory bend at perihelion. I need to be meticulously clear here. This is reported analysis from specific teams, not a universal ironclad consensus. Different observation groups use different modelling approaches, different margins of error. Science is a process of triangulation. But here's the critical point. Multiple independent analyses, using different data sets and methods, keep arriving at numbers clustering tightly around this 16.4-degree figure. It's that consistency emerging from the noise that makes people nervous. 16.4 degrees is not, by itself, anomalous. Objects deflect. That's normal. What is categorically not normal is what that number appears to relate to. 3I Atlas has been exhibiting what astronomers term non-gravitational acceleration. It is speeding up and slowing down in ways that the sun's gravity alone cannot explain. This, too, has precedent with comets. It's usually attributed to outgassing. As solar heating vaporizes ice, the erupting jet of gas acts like a natural thruster, nudging the comet this way or that. But the devil, as always, is in the details. In 3I Atlas, this acceleration appears to be coming from a focused jet of material pointing sunward, not away from the sun, which is what comets almost universally do when solar heating causes sublimation. This jet is aimed toward the solar furnace. Analysis suggests this jet has an opening angle of approximately 8 degrees. Now follow this arithmetic. 16.4 divided by 2 is 8.2. The gravitational deflection angle is almost exactly twice the jet opening angle. That's not close. In the chaotic, messy realm of cometary physics, that is eerily, unsettlingly precise. It is a ratio that whispers of calibration. Precision in a system that should be governed by stochastic, turbulent processes is the sound of alarm bells that scientists are trained, by discipline and temperament, not to ring too loudly. But you can see them listening intently, faces lit by the glow of their monitors. Here's a metaphor to make this click. Imagine you're throwing a ball, and as it arcs through the air, it releases a thin stream of water behind it. Normally, that water spray goes everywhere. It tumbles, disperses, fans out in a chaotic mist, following the complex rules of fluid dynamics. But what if the stream stayed perfectly aligned with the ball's trajectory, a laser straight line of water cutting through the air? And what if the angle of that stream adjusted in real time, moment by moment, to match precisely the curve of the throw? You'd stop thinking about water pressure and gravity. You'd start thinking about intent. You'd suspect a mechanism inside the ball. That is what this 2.1 ratio suggests. It suggests that as 3I/Atlas bent around the sun under immense gravitational stress, its jet, its source of non-gravitational thrust, adjusted its orientation to maintain this specific geometric relationship. The term being used very carefully almost in a whisper. In some of the more daring technical discussions is perfect handoff. Gravity changes the object's path, the jet compensates, the orientation stays locked. The two forces are in conversation. Random outgassing does not do this. Comets are famously chaotic. They tumble, they spin erratically. Their jets flicker, wobble, precess, shut off, and reignite based on which patches of dirty ice rotate into the sunlight. Their geometry is, by its very nature, a study in instability. Maintaining a symmetric, clean mathematical relationship like a 2.1 ratio through perihelion, where gravitational forces are at their absolute strongest and rotational dynamics are most violently unstable, is akin to keeping a spinning top perfectly upright while someone is actively and violently shaking the table underneath it. It's not just difficult, it seems to violate the expected physics of such a small natural body. Let me explain why symmetry through perihelion is such a monumental red flag. As an object approaches the sun, it's not just being pulled forward, it's being twisted. Gravitational torque doesn't just change velocity, it wreaks havoc on angular momentum, orientation, spin state. For a natural body, especially one that's already tumbling and outgassing unevenly, perihelion is a blender. Everything gets scrambled. The object should emerge on the other side with a new rotation rate, a new spin axis, its jets, if they're still active, pointing in completely different, unpredictable directions. That is normal. That is what the cosmos does. But if you come out the other side with your orientation preserved, with your jet still pointing in a direction that makes precise geometric sense relative to your new trajectory, that means something resisted the scrambling, something maintained attitude control through the chaos. Gravity is supposed to be the ultimate explanation for weird trajectories. It's the universal get-out-of-jail-free card for anything moving strangely in space. Gravity did it is often the end of the discussion. But when gravity itself becomes part of a pattern instead of the explanation, when it seems to be incorporated into the object's behaviour rather than dictating it passively, that's the moment you have to stop looking for natural causes and start asking a different class of questions. You have to consider if the object is using gravity, not just experiencing it. This is what Loeb means when he talks about the geometry not lying. You can argue about interpretation all day long. You can debate whether the jet is artificial or some bizarre natural phenomenon. You can question the precision of the measurements until you're blue in the face. But you cannot argue with the persistent appearance of this 2.1 ratio without proposing a mechanism that would naturally produce, and more importantly, maintain it. And so far, no one has proposed a natural mechanism that doesn't involve either an extraordinary 1 in a trillion coincidence or some form of active, feedback-driven control. The silence on that front is deafening. Here's where the intellectual discomfort blooms into something deeper. If the jet's opening angle adjusted to match half the deflection angle, that implies the adjustment happened in response to the changing gravitational environment. That's not just simple thrust. That's navigation. That's using gravity as an instrument, as a tool to be worked with, rather than as a force to be passively endured. And natural objects do not navigate. They drift. They fall. They react blindly. They do not plan. They do not execute a perfect geometric handoff between forces. The alternative, of course, is that this is all a magnificent coincidence. That we are seeing patterns in the noise, finding faces in the clouds, that the 2:1 ratio is an artifact of measurement error, or selective attention, or our profound human wish for the universe to be more interesting than it is. Maybe. Coincidences happen. But coincidences have a cost, a statistical debt. Every time you invoke pure chance to explain a complex, precise observation, you're spending from a limited budget of credulity. 1 coincidence is free, 2 is plausible, if eyebrow-raising. But when you get to 15 independent, interconnected anomalies, as we will see, it starts to look less like chance and more like a confession. The universe is trying to tell us something. And if maintaining this kind of orientation through the gravitational meat grinder of perihelion is possible, if it happened once, then logic dictates it's been happening the entire time, which forces us to talk about the sheer engineering difficulty of the next anomaly, keeping something pointed relentlessly at the sun for months on end, while the gravity of the solar system tries to spin it like a tossed coin. This relentless, unblinking focus is called continuous sunlock, and it is arguably the most technically damning piece of behaviour we've witnessed. If the 16-degree problem hints at navigation, sunlock screams of purpose. Spacecraft engineers have a sobering maxim: pointing is harder than pushing. That isn't casual intuition, it's brutal experience bought with decades of failed missions, blown budgets, and heartbreak over lost probes. You can strap a rocket engine to almost anything and make it go faster. That's Newton's third law, straightforward in principle. But making it go faster while keeping it facing the exact right direction, that's where aerospace engineering graduates from physics to an art form, and where the costs skyrocket. Here's why. In the vacuum of space, there's no friction, no air resistance, nothing to naturally damp out a rotation or a wobble. If something starts spinning, it keeps spinning. Forever. If it develops a wobble, that wobble persists, often compounding. And everything out there is spinning, because everything got to its current state by bumping, colliding, and aggregating over billions of years. Every collision imparts angular momentum. Natural bodies, asteroids, comets, random debris, they tumble. They tumble in complex, chaotic ways, sometimes rotating around multiple axes simultaneously in a drunken, unpredictable pirouette. This is called passive tumbling. It is the default, the natural state of small objects adrift in the cosmic sea. Controlled attitude is something else entirely. That's when an object maintains a specific, stable orientation relative to an external reference point, like the Sun, or Earth, or its direction of travel. Satellites do this. Spacecraft do this. They do it with reaction wheels, gyroscopes, tiny thrusters, and millions of lines of code governing, careful planning, and constant micro-adjustments. And even with all that technology, they drift. Attitude control is not a set-it-and-forget-it proposition. It is an ongoing, energy-intensive battle against the universe's inherent tendency toward rotational chaos. It requires constant energy expenditure, sensors, computation, and something. An algorithm, a brain, making decisions to correct course. It implies a goal. 3i Atlas has, according to the observational data, maintained a sunward-facing orientation for months. Not approximately sunward. Not occasionally sunward. Consistently, precisely locked on target. It has done this while tumbling through the void, while undergoing that severe gravitational deflection, while allegedly outgassing, while being a comet-like object that should, by all rights and precedent, be spinning like a drunk penguin on an ice floe. This is not a fleeting anomaly, it's a sustained behaviour. And in the language of engineering, sustained behaviour against entropy requires a system. There's a concept in spacecraft design called a pole switch. It's a deliberate manoeuvre where you flip your orientation by 180 degrees, usually to manage thermal loads, reorient solar panels, or point instruments in a new direction. It requires planning and control. You have to spin down your current rotation, execute the flip using thrusters or momentum wheels, and then stabilize in the new, desired orientation. Loeb has speculated, with characteristic caution, that 3i Atlas might have performed something analogous. Not because we saw the fiery plumes of thrusters, we didn't, but because the before and after orientation data, when fed through the models, suggests such a flip is the simplest explanation for how it maintained its sunlock through a particular orbital segment. The object seems to have executed a course correction that looks for all the world like a planned manoeuvre. Let me explain angular momentum damping without equations. Imagine you're sitting on a spinning office chair. You're rotating. To stop rotating, you need to push against something external, the floor, a desk, a wall, something that can absorb your angular momentum. In space, there is nothing to push against. So, to change your spin, you have to throw something. You eject mass in one direction, and conservation of momentum spins you in the other. Comets do this accidentally through asymmetric outgassing. Spacecraft do it deliberately with precisely aimed thrusters. But here's the profound problem. Random, natural outgassing creates random torque. It might speed you up here, slow you down there, tilt you in unplanned directions. It's like trying to stop a spinning office chair by randomly throwing tennis balls in every direction. You might eventually slow down through sheer statistical luck, but you are absolutely not going to end up facing a specific, predetermined compass point. And you are definitely not going to stay facing that exact point, motionless, for months afterward. Natural bodies, especially after the gravitational violence of perihelion, should be rotationally scrambled. Gravitational torque does not preserve orientation, it disrupts it. Think again of the spinning coin. Now imagine shaking the table violently while it spins. The coin doesn't keep its axis stable. It wobbles, precesses, and falls. Perihelion is the shake. The fact that 3I Atlas came out the other side still perfectly sunlocked means something actively resisted and cancelled the wobble. You can try to propose a natural mechanism for that resistance, but the burden is on you to explain how. You have to show how random outgassing, random mass ejection from a volatile, inhomogeneous surface could consistently and precisely produce torque vectors that correct for gravitational perturbations in real time. That is not a simple mechanism, that is a control system. That's feedback. That is sensing your orientation, comparing it to a target run, calculating the error, and adjusting your thrust to minimize that error. Natural objects do not do feedback. Ice sublimating in sunlight does not have a target. It just happens. Here's another way to think about it, a more philosophical lens. Motion can be accidental. Orientation implies purpose. If something is moving fast, maybe it was hit. If something is accelerating, maybe it's shedding gas. But if something is maintaining a specific energy-costly orientation over an extended period, despite environmental forces trying to knock it off course, that suggests the orientation itself matters. That there is a reason for it. That facing the sun specifically serves a function important enough to justify the expended energy. What function? The usual suspects for a spacecraft: power collection, thermal management or cooling critical systems, instrument alignments, sensors pointed at the sun or using it as a reference, or communication, using the sun as a beacon or a shield against interference. A comet has no need for any of that. A comet doesn't care where it faces. Let me address the most common natural counter-argument head-on, because it's a good one. Maybe, just maybe, the object has a highly asymmetric shape or an uneven mass distribution that naturally stabilizes it in a sun-facing orientation through something like radiation pressure or thermal effects, a kind of wind vane or shuttlecock effect in the solar wind. Okay. Maybe, but for that to work, several extraordinary things must be true simultaneously. First, the asymmetry has to be significant enough to overcome the relentless, chaotic tumbling induced by gravitational torque and outgassing. Second, it has to be aligned in exactly the right way from the start. Third, this delicate balance has to persist completely unscathed through the gravitational maelstrom of perihelion. And fourth, this same lucky asymmetry must also somehow explain the coherent jet, the 201 trajectory relationship, the compositional anomalies, and the timing. You are no longer proposing one simple mechanism. You are proposing a cascading series of fortunate circumstances, a Rube Goldberg machine of natural luck, where each unlikely event depends on the previous one. Each one individually improbable, all of them aligning perfectly to mimic, in every observable detail, the behavior of a deliberately controlled probe. At a certain point, the natural explanation becomes vastly more complicated and statistically implausible than the artificial one. And that's a deeply uncomfortable corner for science to be in, because we are culturally trained to prefer natural explanations, even when they require intellectual gymnastics that would make a contortionist wince. Occam's razor tells us to prefer the simpler explanation, but we have, somewhere along the line, confused simpler with more familiar. A manufactured object is a familiar concept. The idea that it's an alien artifact is not. So we reject the familiar solution because the origin is unfamiliar, even if it makes the data itself simple to explain. So, if orientation control is this hard, if it requires this level of precision and energy, then why do it? What's the payoff? Why would something go to all this effort to keep facing the sun, unless facing the sun was the entire point? Unless the orientation itself was the mission, not a side effect? That question leads us into territory that makes institutional science profoundly nervous, because once you start asking why, you are assuming intent. And intent is the third rail of this entire conversation. Touch it, and everything explodes into debates about burden of proof, extraordinary claims, and the limits of science. But the data has brought us here. We might as well follow it. What if the most logical explanation is also the most profound? And what if part of its logic is to look exactly like something it's not? What if looking natural is not a coincidence, but the core strategy? This brings us to the Trojan Horse hypothesis, and it's here that we move from analysing behaviour to inferring strategy, a speculative but terrifyingly logical leap. The Trojan Horse isn't a metaphor, it's a strategic archetype. Imagine you are a civilization that wants to send a reconnaissance probe to another star system. You face a monumental problem. The destination civilization might have detection capabilities you can't predict. They might see you coming from light years away. They might classify you as a threat and intercept or destroy you. They might simply ignore you as irrelevant. Your primary goal is to get close enough to gather high-quality data without triggering defensive or dismissive responses. So, what is your optimal strategy? You camouflage the probe. You dress it in something the locals will automatically classify as harmless, as background noise. You wrap its core structure in ice and dust. You let it accrete a thick, convincing coating over millions of years of interstellar travel, so it arrives looking like every other piece of cosmic debris wandering through their system. You make it look, from a distance and at first glance, like a comet. This is the Trojan Horse hypothesis in its purest form. I want to be excruciatingly clear. It is a hypothesis, a scenario constructed to explain the observations if those observations are accurate. It is a thought experiment about interstellar reconnaissance logistics. But it is also disturbingly, compellingly logical once you think through the practical engineering constraints of an ultra-long-duration space mission. Here's why a natural exterior isn't just clever, it's almost inevitable. If you're travelling for millions of years through interstellar space, you are not moving through a perfect vacuum. You're moving through a medium containing sparse gas, dust grains, and micrometeoroids. Everything out there gets sandblasted, pitted, and coated over geological timescales. A probe launched from a distant star wouldn't arrive in our solar system looking shiny, polished, and metallic. It would arrive looking weathered. It would look like it's been on an epic journey, because it has. A million-year journey through the galaxy's gentlest, slowest version of weathering. This accumulated crust isn't a flaw, it's perfect camouflage, and it explains a lot. It explains why 3I/Atlas reflects light spectroscopically like a comet, but behaves like something else entirely. It explains why surface chemistry appears comet-like, while the underlying dynamics suggest rigid internal structure. It's not active deception. It's just time and physics doing what they do to everything, leveraged as a shield. But there's a specific detail in the spectroscopic reports that elevates this from mere speculation to a pointed question. 3I Atlas's water-to-dust ratio, based on some observational campaigns, appears inconsistent with normal cometary values. Again, precision is key. This is from specific analysis, not a unanimous verdict. But if these numbers hold, the object is shedding material in proportions that don't match the expected recipe for simple ice sublimation. Comets have a standard profile, They are dirty snowballs, specific mixtures of water ice, rock, frozen gases, and organic compounds. When heated, the ice sublimates, turning directly to gas, and carries embedded dust grains with it in predictable, well-understood ratios. By analysing the spectrum of the coma, the cloud of material around the comet, we can measure this ratio, which tells us about its internal composition. If the ratio is off, it means something unusual is happening. Either the internal composition is exotic, requiring a strange formation history, or the material being shed isn't coming from passive ice sublimation alone. It could be coming from surface erosion, or from structural shedding, or from material being deliberately ejected for propulsion or attitude control. Think about using mass ejection for propulsion from an engineering perspective. You don't necessarily want to eject pure water vapour. Water vapour is hard to produce efficiently if you don't have abundant pure ice. And if you do rely on solar-heated ice, you're at the mercy of distance from the sun and surface rotation. It's an unreliable throttle. What you'd want is a propellant you can control, dust, particulates, material you can heat and accelerate efficiently using an internal power source. And if your probe is wrapped in a kilometres-thick crust of accumulated interstellar junk, a mix of ices, silicates and complex organics, you have a ready-made abundant propellant supply right there. You just scoop it up, heat it with a reactor or focused energy beam, and eject it. From a distance, through a telescope, it looks like normal cometary outgassing, except the ratios of gas to dust, or the specific chemicals in the plume, are subtly off. The dirty appearance becomes strategically brilliant. If observers see a comet behaving oddly, their first, second and third instinct is to classify it as an odd comet, not a spacecraft. The natural coating provides cognitive cover. It biases the classification engine, the human scientist's brain, toward familiar categories. And that bias is powerful. It takes extraordinary evidence to move an object's classification from weird natural object to potential artifact. Every layer of natural appearance raises that evidence threshold exponentially. Camouflage is a universal strategy across biology, military science, and intelligence. Prey species evolve to blend in to avoid predators, predators evolve to ambush prey. Submarines are designed for acoustic stealth, aircraft for radar cross-section reduction. Spies build convincing covers. There is no reason, none at all, to think a technological intelligence capable of interstellar travel wouldn't use the same foundational principle. If you're sending reconnaissance probes to potentially inhabited systems, you camouflage them as natural objects, because natural objects don't trigger alarm bells. And if your travel time is measured in millions of years, the camouflage applies itself automatically. You just have to design the core probe to survive the accretion process and to be able to use that crust. Now, I can hear the skeptical counter-argument forming. This is unfalsifiable. You're just adding epicycles. Any observation that doesn't fit the comet model gets explained away as part of the disguise. It's a conspiracy theory dressed up as science. That is a fair criticism, and it must be addressed. But the criticism cuts both ways. At what point do we stop adding epicycles and special pleadings to natural explanations? At what point does the weirdest comet ever observed, with 15 independent anomalies, become a less parsimonious, less likely explanation than object with an artificial core and a natural crust? The difference between a baseless conspiracy theory and a legitimate scientific hypothesis is whether it makes testable, falsifiable predictions. The Trojan Horse hypothesis does make predictions. It predicts that the internal structure should differ radically from the external appearance. It predicts compositional gradients, a manufactured core surrounded by a layered accreted shell. It predicts that if we could somehow sample beneath the surface, we'd find materials and structures that don't match cometary genesis. With enough data, perhaps from a dedicated intercept mission, which is now being whispered about in serious circles, we might one day test this. But for now, we are stuck in the profoundly uncomfortable position of having a stack of observations that fit the hypothesis neatly. without being able to definitively prove or disprove it. This brings us back to the overwhelming weight of cumulative evidence, what we call probability stacking. The Trojan Horse idea doesn't stand alone in a vacuum. It's one piece of a larger interlocking pattern of anomalies that either represent the most statistically improbable series of coincidences in the history of astronomy or point to a different conclusion. One strange thing is noise. 15 strange things, all aligning in a way that points to a single coherent alternative explanation. That's a signal. It's a message written in the language of physics and geometry. And we are just beginning to decipher it. Let me tell you how probability actually works in the real world, not in the abstract. If I flip a coin and it comes up heads, that's not surprising. A 50-50 chance happens all the time. Flip it again, heads again? Still normal. There's a 75% chance of getting at least one heads in 2 flips. But if I flip that same coin 20 times, and it comes up heads every single time, you stop thinking about probability theory and start examining the coin. You check if it's weighted. You question the flip. That's probability stacking. Individual events might be explicable in isolation, but when you see correlations, when independent variables start lining up in a way that shouldn't happen by chance, the math ceases to be your friend and becomes an accuser. By conservative count, 3i Atlas exhibits roughly 15 distinct anomalies, depending on how you categorize them. Let's list them. 1. The non-gravitational acceleration. 2. The sunward not Nanyat jet. 3. The 16.4 degree gravitational deflection. 4. The 8 degree jet opening angle and the 2.1 ratio. 5. Sustained precise sunlock orientation for months. 6. Apparent attitude control and possible pole switching maneuvers. 7. Compositional anomalies in metal ratios. 8. Anomalous cyanide levels. 9. A coma weaker than expected for its size and solar distance. 10. Clean, too consistent chemical ratios versus natural variability. 11. A columnated jet maintaining coherence over millions of kilometers. 12. A trajectory that sets up a perfect gravity assist with Jupiter. 13. Its arrival timing in the inner solar system, which was geometrically optimal for the Earth flyby. 14. Its overall light curve and reflectivity profile, which suggests a complex, possibly layered surface. 15. The sheer statistical implausibility of all these rare traits occurring in one object. Each one of these, taken alone, can be explained away with enough creativity and special assumptions. Maybe it has a weird shape. Maybe it's a new type of interstellar object. Maybe our models of outgassing are incomplete. This is what scientists traditionally do. They isolate variables. They look at each anomaly separately, propose a natural mechanism, and if the probability of that mechanism is within often nemerously bounds, they move on. This is good, cautious methodology for most situations. But it fails catastrophically when you are not dealing with independent anomalies, but with a system, when the anomalies are not separate puzzles, but interconnected expressions of the same underlying phenomenon. Think of it this way. If I told you one person won the lottery, you'd think they were lucky. If I told you the same person won the lottery twice, you'd be deeply suspicious. If I told you they won 15 different independent lotteries, you would no longer entertain the concept of luck. You'd assume fraud. The same principle applies here. Let's say each individual anomaly has a 1 in 100 chance of occurring, naturally alongside the others, a generous estimate. The chance of all 15 occurring together? That's 1 in 115. That is a number so astronomically small, it is functionally zero. It's less likely than randomly assembling a 747 by a tornado blowing through a junkyard. Navigation systems don't arise by accident. Precision orientation control doesn't happen by accident. Persistent geometric relationships through gravitational chaos don't happen by accident. Clean industrial chemistry, timing coincidences, trajectory adjustments that anticipate gravity wells, these things individually stretch credulity. Together, they shatter it. And yet, here we are, still having this conversation as if the natural explanation is the default null hypothesis position. Why? Because admitting the alternative is psychologically and professionally unbearable for many. It means our understanding of our place in the cosmos, of who or what might be out there, of whether we are alone, all of it is thrown into instant, dizzying question. Humans are experts at not noticing or aggressively rationalizing things that would force a catastrophic update to our worldview. Psychologists have a term for this: normalcy bias. It's the tendency to underestimate the probability of a disaster, to assume tomorrow will be like today, that the patterns we've always known will continue indefinitely. It's why people ignore evacuation orders before a hurricane. It's why investors dismiss warning signs before a market crash. It's why entire civilizations collapse even when the evidence of decline is obvious in hindsight. Black swans thrive in the fertile ground of normalcy bias. They happen in the widening gap between what the data is screaming and what we are willing to believe. And the people who point at the gap are always initially dismissed as alarmists, paranoids, or pattern seekers drowning in noise, until the moment they are vindicated, and it's too late. History is littered with these failures of pattern recognition. The evidence for continental drift was obvious from the map. The coastlines fit together like puzzle pieces, but geologists rejected it for decades because they couldn't conceive of a mechanism. Meteorites were dismissed as peasant folklore, or atmospheric condensation, rocks do not fall from the sky, was a scientific consensus. The heliocentric model was resisted not because the math was wrong, but because it displaced humanity from the centre of God's creation. The pattern is clear: paradigm shifts don't occur when new evidence arrives. They occur when the community, worn down by the sheer weight of that evidence, finally becomes ready to accept what it has been saying all along. We might not be ready yet. We might need more data, more time, more independent confirmation. Or we might right now be in the final hours before that shift happens. A year from now, everyone reading this might look back and wonder how the truth wasn't blindingly obvious. That is the nature of the black swan. It is invisible until the moment it isn't. You can't see it while you're in the before time, because your entire cognitive framework for understanding reality doesn't yet contain the category for it. It's not that the evidence is hidden, it's that the mental software required to process that evidence hasn't been installed. So, we return to the central throbbing question, the only one that truly matters tonight. Are we watching a natural object with an unprecedented bundle of weird properties, or are we watching something that was designed to look like a natural object, where the weird properties are the subtle places where the design, the intent, inevitably shows through? I don't know. Loeb doesn't know. No honest scientist claims to know. Anyone who offers you certainty in either direction at this moment is lying to you or to themselves. But the question is on the table now, vibrating with implications. It will not go away just because it makes us uncomfortable. And if there is even a 1% chance, even a 0.1% chance, that this hypothesis is correct, then the object's trajectory after Earth becomes the most important thing we could possibly be tracking. Because maybe Earth was never the final destination. Maybe we were just a waypoint, a target of opportunity on a longer journey. Maybe the real mission, the strategic objective, is what comes next. And where is it going next? It's heading straight for the solar system's gravitational powerhouse, Jupiter. And in orbital mechanics, Jupiter is never just the next stop. It's the key to everything. In the popular imagination, the solar system is often pictured as a series of destinations. Mercury, Venus, Earth, Mars, stops on a grand tour. But this is a profound misunderstanding of orbital mechanics, a tourist's map that ignores the underlying infrastructure. In reality, trajectories aren't primarily about where you're going, they're about what you're using. And in our solar system, Jupiter is the ultimate piece of infrastructure. It is the gravitational anchor, a titan with 318 times the mass of Earth, a magnetic field 14 times stronger, and a sphere of gravitational influence that extends millions of kilometers into space. When human mission designers plot journeys to the outer solar system and beyond, Jupiter isn't just a destination, it's a slingshot, a brake, a pivot point. It is the tool you use to go places that would otherwise be unreachable, or to change your mission profile without expending a prohibitive amount of precious fuel. 3i Atlas's trajectory, after its close approach with us, takes it on a path toward Jupiter. On the surface, this sounds mundane. Many objects pass through the inner solar system and head outward. But it's the geometry of this path that matters, the precise approach angle, the velocity at arrival, the timing relative to Jupiter's own position in its orbit. These parameters aren't random. They are what engineers call a gravity assist setup. You arrive at a specific point, at a specific speed and angle. Jupiter's immense gravity bends your trajectory like a stone in a sling, and you leave with an altered velocity and direction, sent towards some final goal. It's free propulsion, the ultimate cosmic hack. I need to be scrupulously careful here. Natural objects can and do end up on gravity assist trajectories by pure chance. The solar system is a dynamic, chaotic place, and sometimes things line up. But when you combine a precise gravity assist setup with all the other anomalies, the apparent navigation, the sustained sunlock, the compositional oddities, it stops looking like a random outcome of chaos and starts to look like a flight plan. The trajectory ceases to be something that happened to the object and begins to look like something the object is executing. This brings us to what makes Jupiter particularly interesting from a strategic perspective. Jupiter has what is known as a Hill sphere, the region of space where its gravity dominates over the sun's. Inside this vast volume, objects can be captured into stable orbits around Jupiter itself. Outside it, they remain in orbit around the Sun. The boundary between these zones is a realm of complex, beautiful chaos, where three-body dynamics reign. It is here that you find gravitational sweet spots known as Lagrange points, positions where the gravitational pulls of Jupiter and the Sun balance perfectly, allowing a third, much smaller object to maintain a stable position relative to both giants with minimal energy expenditure. Earth has Lagrange points. The James Webb Space Telescope sits at one. The Sun-Jupiter system has its own set, and they are some of the most stable and useful in the solar system because of Jupiter's sheer mass. Lagrange points are prime celestial real estate. They are perfect for observation platforms, communication relays, or long-term monitoring stations. Any mission where you need to park and maintain a steady position without constant, fuel-guzzling corrections. Now consider this. If you were planning a long-term reconnaissance mission in someone else's star system, where would you place your assets? You would want persistent surveillance. You would want to leave behind something that could keep watching long after the main probe has moved on. The Lagrange points of the system's most massive planet, offering a stable vantage point, would be an obvious, perhaps ideal choice. Let me be unequivocally clear. There is zero direct evidence that 3i Atlas is planning to deploy anything at Jupiter's Lagrange points. This is informed speculation, a scenario based on trajectory geometry and logical inference. It is what human mission planners would consider if we were sending a robotic reconnaissance probe to another star. You don't stop. You don't land. You fly through, you gather high-value data during your close pass, and you leave behind small, stealthy assets in stable positions for long-term observation. It's the difference between a one-time spy satellite flyover and establishing a permanent surveillance network. Think about our own history of using gravity assists. Voyager 1 and 2. Cassini. New Horizons. Every single major mission to the outer solar system has used Jupiter as a gravitational stepping stone. Not because we were obsessed with Jupiter, but because it was pragmatically essential. It provided the velocity change needed to reach Saturn, Uranus, Neptune or Pluto within a human lifetime. It's free delta V. If you have the capability to navigate precisely, you use it. And here is the most quietly unsettling part of this Jupiter scenario. If 3i Atlas approaches Jupiter's Hill sphere at the precise angle and velocity implied by its current trajectory, it could, in theory, release one or more smaller objects, subprobes, sensors, relays that would gently detach and be deposited into stable orbits or Lagrange points, while the main body continues on its way, perhaps toward interstellar space once more. Those released objects would be tiny, dark, emitting no signals, passively observing. They would be virtually invisible unless we were specifically and meticulously looking for them in exactly the right places. They would just sit there, in gravitationally stable positions, watching the inner solar system and Earth for millennia. I can hear the objection rising, this is pure science fiction. This is conspiracy theory thinking. And I understand that reaction. It sounds outlandish. But hold that thought and consider the alternative premise for a moment. If this is a technological object, if it originated from another civilization, what would a sensible, conservative mission profile look like? Would it land on the White House lawn? Would it broadcast greetings on a common frequency? Or would it do exactly what we do and what we plan to do with our own proposed interstellar probes? It would observe quietly. It would gather data without contamination or disruption. It would avoid detection until it understood what it was dealing with. It would prioritize the longevity and success of the mission over dramatic contact. From this perspective, Earth may have been a primary target for a close-range scan, a chance to measure our atmosphere's biosignatures and technosignatures, to map our radio emissions and city lights. But Jupiter could be the strategic objective. Jupiter is where you establish your long-term presence. It is the difference between a reconnaissance flyby and the deployment of a surveillance network. Earth gets the close-up photo, Jupiter gets the hidden security camera that keeps recording. Before you dismiss this as fantasy, remember we are already designing missions based on this logic. Projects like Breakthrough Starshot or NASA's Interstellar Probe concept all involve flying past a target star system at a significant fraction of light speed, deploying small chip-sized probes to collect data during a blisteringly fast flyby, and beaming that data back home. The idea of a fast, observant flyby followed by data transmission is not alien, it's human. It's logical. The timing, once again, feels pointed. 3i Atlas arrived in the inner solar system at a moment when Jupiter's position makes this specific gravity assist geometry possible. Had it arrived 6 months earlier or later, the angles would have been wrong. You can, again, call this coincidence. But as the probability stack grows taller, the foundation of coincidence begins to crumble under the weight. How many perfect coincidences are we willing to accept before the explanation itself becomes untenable? So, if Earth was the target of a high-resolution scan, and Jupiter is the site of potential infrastructure deployment, what then? Where does the main body of 3i Atlas go after Jupiter? And more importantly, if it does leave something behind, how would we ever know? The sobering answer is, we probably wouldn't. Not unless we mounted a dedicated, intensive search of Jupiter's orbital realms, specifically targeting its Lagrange points with our most sensitive telescopes and looking for objects that shouldn't be there. And even then, something designed to avoid detection would likely be very, very good at it. But the possibility is now part of the equation. The hypothesis is on the table. And perhaps that in itself is a kind of breakthrough. Maybe the true signal from 3i Atlas isn't a radio transmission or a flashing light. Maybe the signal is the set of questions it forces us to ask, questions about what could be lurking in our own celestial backyard that we've never thought to look for. However, while trajectories and geometries can be argued, there is another line of evidence that is harder to dismiss with hand-waving. It's the forensic evidence etched in light itself. Chemistry. And chemistry, unlike complex orbital dynamics, has a stubborn, non-negotiable quality. Elements and molecules must obey their own rules. They can't easily pretend. Comets are supposed to be messy. They are not precision-engineered objects. They are the leftover construction materials of a solar system, the dirty snowballs and icy mudballs that never got swept up into planets. Their chemistry reflects that chaotic origin. They are inconsistent, varied, full of a wild array of organic molecules and trace elements in ratios that fluctuate from one comet to the next. This messiness is their signature. It tells a story of formation in cold, dark regions where chemistry proceeded slowly and unevenly over millions of years. So, when a comet-like object shows up displaying clean ratios, consistent compositions, a chemistry that looks more manufactured than accumulated, it stands out like a polished diamond in a pile of rough gravel. It breaks the pattern. The spectroscopic analysis of 3I Atlas, breaking its reflected light into a chemical fingerprint, has revealed several such breaks in the pattern. As always, this is based on reported data from specific observational campaigns. It is the cutting edge of analysis, not settled textbook fact. But the flags raised by multiple, independent teams are all pointing in the same disquieting direction, toward consistency where there should be variety, and toward specific anomalies where there should be solar system norms. Let's start with metals. Nickel and iron. These are common elements in the cosmos, present in asteroids, in the rocky cores of comets, and in interstellar dust. But they exist in specific ratios that act as a forensic tracer. The nickel to iron ratio in a body depends on the temperature, pressure, and chemical environment of the nebula where it condensed. Natural processes produce a range of ratios bounded by the laws of physics and chemistry. The nickel to iron ratio inferred from some of 3I Atlas's spectroscopic measurements appears to sit just outside the expected range for objects that formed in our own solar system. Not wildly outside, not physics breaking, but outside. Enough to force a double check of the calibration. Enough to make you wonder, did this object form somewhere else? Under different stellar conditions, or is this ratio telling us less about origins and more about processing? Because when you find an anomalous ratio, it can mean an exotic birthplace. But when you find an anomalous ratio that is also precise and consistent, it starts to hint at refinement. Here's why that distinction matters. Industrial processes are designed to produce consistency. Smelting, alloying, purification, any intentional material processing drives towards specific stoichiometric values because you are optimizing for a desired property, strength, conductivity, durability. Natural processes, operating over astronomical timescales, produce distributions. They produce scatter plots. If you find a single rock on Earth with an unusual metal ratio, you might conclude it's a meteorite from an unusual parent body. But if you find 10 rocks, all with the exact same unusual ratio, you stop thinking about geology and start thinking about a smelter. You think about a stockpile. Then there's the matter of cyanide. Hydrogen cyanide is common in comets. It forms readily in the cold, dark molecular clouds that birth stellar systems. Comets typically have cyanide abundances within a certain predictable, if variable, range. Too much, and you need a special environment to explain it. Too little, and you need a process that destroyed it. 3I Atlas shows cyanide levels that some observers describe as anomalous, higher than typical, but not in a way that neatly matches the patterns of known comets. Cyanide is interesting not just as a fossil molecule, it is also a potential propellant precursor, a building block for certain types of energetic chemical reactions. If you were engineering a long-duration probe that needed to manufacture thrust or power from locally available materials like that accumulated crust, hydrogen cyanide chemistry could be part of your toolkit. I am not saying 3I Atlas is leaking rocket fuel. I am saying the chemical signature is unusual, and its unusual nature is consistent with either exotic natural formation or with deliberate chemical engineering. Both are possible. Neither is confirmed, but the pattern, anomalous, precise and functional, keeps repeating. Let me crystallize the concept of clean versus messy. When you survey a population of comets, their chemistry is like a crowd of fingerprints, all unique. Comet A has more water, less carbon monoxide. Comet B has more methane, a different dust composition. This variability is expected. They formed in different parts of the protoplanetary disk, at different times, from slightly different mixes of the primordial soup. Now imagine you found 100 people with identical fingerprints. You would instantly abandon the idea of natural variation. You'd think of cloning, or manufacturing, or a process imposing a template. That is what is being detected in 3i Atlas's chemistry. It's not that any single measurement is impossible for a natural object. It's that the collective suite of measurements suggests less variability than the chaos of nature should allow. More consistency. More precision. And precision in chemistry is almost always a hallmark of control, of processes operating within narrow parameters to achieve a specific outcome. Blast furnaces produce consistent steel because temperature, pressure, and timing are controlled. Nature, left to its own devices over millions of years, produces a spread. Randomness accumulates. Entropy has its way. If 3i Atlas's composition hints at control, that's another heavy weight on the probability stack. It's chemistry now whispering the same story that geometry and dynamics have been shouting. And chemistry is brutally honest. It's hard to fake. You can coat an object in dust, but that dust has its own spectral signature. You can hide a core, but the material you eject, the coma, carries the imprint of what's inside. If the ratios are wrong for a simple dirty snowball, they are wrong. A coating of cosmic dust doesn't change your internal stoichiometry. There's also the telling clue of what we are not seeing. Comets are defined by their comas, the expansive, glowing clouds of gas and dust that form when sunlight vaporizes their ices. The coma is how we do our chemical detective work. We analyze its light. 3i Atlas has a coma, but it is anomalously faint and thin for an object of its estimated size and its distance from the Sun. This could mean it has very low volatile content unusual for such strong non-gravitational acceleration. It could mean its surface has unusual thermal properties. Or it could mean the outgassing isn't being driven primarily by passive solar heating. If you are using an internal energy source to deliberately heat and eject material for propulsion or attitude control, you are not creating the broad, diffuse coma of a sublimating ice ball. You are creating a more focused, efficient plume. It would look comet-like, but not quite behave like one. The pieces keep fitting together, forming a picture that is increasingly difficult to reconcile with a simple, natural, icy body. So, we have metal ratios that are unusual, cyanide levels that are unusual, a coma that's unusually weak, an overall composition that's unusually consistent. Each one can be explained in isolation with a suitably contrived natural story. All of them together, however, begin to paint a portrait not of formation chemistry, but of something that looks suspiciously like industrial chemistry. And if the chemistry hints at industry, then we must look with fresh eyes at the most glaring industrial-looking feature of all, the beam. The narrow, sustained, coherent jet of material that seems to defy the natural behaviour of cometary outgassing. What we assumed might be propulsion might be something far more specific. Comet jets are chaos made visible. When a patch of volatile ice on a comet's surface sublimates, the gas erupts through cracks and fissures, expanding rapidly into the vacuum and carrying with it a spray of dust particles. These plumes are typically wide, diffuse and turbulent. They interact with the solar wind, are sculpted by magnetic fields, and form the iconic tail that always points away from the sun. It's a beautiful, messy process. The jet observed on 3i/Atlas is something else entirely. It is not diffuse, it is collimated, a technical term meaning it forms a narrow columnated beam. Analysis suggests this beam maintains its coherence over staggering distances, potentially up to 1 million kilometers. This is not normal. Gas expanding freely into a vacuum should spread out rapidly, its density decreasing with the square of the distance. It should diffuse, dissipate, and lose all definition. Think of smoke from a candle. Right at the wick, it's a thin stream. Just a few centimeters away, it has already billowed out, mixing with the air and losing its shape. Now imagine that smoke staying in a perfectly straight, pencil-thin column for an entire kilometre. That's the level of anomaly we're talking about, scaled up to a cosmic level. Collimated jets require one of two things: either a specific nozzle geometry that physically constrains and directs the flow as it exits, or an external force like a magnetic field that focuses the material after it has been ejected. Nozzles are engineering. They are designed. Magnetic collimation requires the ejected material to be ionized, turned into, and requires a strong, carefully shaped magnetic field to contain it. Neither a natural nozzle nor a sufficiently powerful and organized magnetic field is something we expect from a small, supposedly primordial icy body. Both explanations push the boundaries of natural plausibility. Let's break down what it takes to maintain a coherent beam over 1 million kilometers. First, you need a sustained and consistent source of ejected material. This implies a reservoir that doesn't run out quickly and an ejection process that doesn't fluctuate wildly. Comets are notoriously variable. Their jets flicker and pulse as different ice patches rotate in and out of sunlight. A steady, unwavering jet requires either a massive, homogeneous volatile reservoir or a process of continuous replenishment and controlled release. Second, you must actively prevent dispersion. Molecules in a gas have random thermal motion. Even if they are ejected in the same general direction, this randomness causes the beam to spread. To keep it tight, you need the molecules to be moving very fast in the intended direction compared to their random thermal velocity, which implies high, controlled ejection speeds, or you need something to shepherd them, to guide them along the path. High ejection velocity from simple solar heating is difficult. You're limited by the energy available from sunlight. You might get a few 100 meters per second under ideal conditions. To maintain collimation over 1 million kilometers, you'd need significantly higher velocities, or you'd need that guiding mechanism. This is where speculative but informed engineering thinking comes in. If the jet is somehow shielded from the disrupting influence of the solar wind, perhaps by a magnetic or electrostatic bubble, you could maintain its coherence over vast distances. We use magnetic nozzles in some advanced ion thrusters for precisely this reason, to create a magnetic bottle that channels plasma, keeping it focused to maximize thrust efficiency. Could a natural object do this? Possibly, if it had an intrinsic powerful magnetic field and just the right geometry. But most comets and asteroids are too small and insufficiently differentiated to generate a global magnetic field. There's no dynamo action in a lump of ice and rock. So, to explain a collimated jet naturally, you'd have to propose that 3I Atlas is yet again extraordinary in another unique way. It possesses magnetic properties comets don't have, and those properties are perfectly configured to create a beam. Or you accept that the jet's properties are being managed. Then there's the direction. The jet points sunward. This is critically important. For a comet heated by the sun, outgassing should be strongest on the sun-facing side, and the resulting thrust should push away from the sun. A sunward-pointing jet would be like a rocket firing toward the ground while you're trying to lift off. It would push the object toward the sun, slowing its approach. But 3I Atlas's trajectory doesn't show the clear deceleration signature you'd expect from such sunward thrust. Instead, it shows a more complex pattern of acceleration and deceleration that seems coordinated with its orbital position and orientation needs. This is the key distinction between propulsion and maneuvering. Propulsion is about changing your speed in your direction of travel. Maneuvering is about changing your direction, maintaining your attitude, fine-tuning your path. Maneuvering requires a control system. It requires sensors to know your orientation, computers to calculate the needed corrections, and actuators to execute them. You cannot maneuver by accident. A natural outgassing jet is blind propulsion. What we seem to be seeing is targeted maneuvering. This leads to a radical reinterpretation. The beam might not be for primary propulsion at all. It might be a reaction control system, akin to the tiny thrusters on a satellite that fire briefly to maintain its pointing, not to speed it along its orbit. You're not trying to go faster, you're trying to stay aimed correctly while you coast. And if your mission requires you to stay aimed at the sun while your trajectory bends violently around it, you need continuous, minuscule, precise adjustments. Using mass ejection for precise attitude control is standard spacecraft engineering. But it is not geology. It is not cometry science. Natural objects do not stabilize their orientation by ejecting material in carefully calculated, continuously adjusted directions. They tumble. They obey chaos. Stability in this context implies intent. And again, we circle back to the haunting question, why? If you are using precious reaction mass, the stuff of your own body, to maintain this perfect sunlock, that mass must be buying you something absolutely vital. What is so important about facing the sun that you dedicate your entire mission profile to it? The answers from an engineering standpoint are obvious: power, thermal management, communication, or instrument alignment. Solar panels need to face the sun. To avoid freezing or overheating, you need to manage which sides are illuminated. To communicate with home, you might use the sun as a positional reference or as a gravitational lens for your signal. Your primary sensors might be mounted on the sun-facing side. These are spacecraft design considerations. They are not the concerns of a lump of ice. If 3i Atlas is maintaining sun pointing for any of these reasons, then we have decisively crossed the line from comet to craft. But perhaps I'm getting ahead of the evidence. Maybe all of this, the trajectory, the chemistry, the beam, is just an extraordinary series of natural phenomena we've never seen before. Maybe 3i Atlas is simply teaching us that the universe is far stranger, far more capable of producing complex, seemingly designed phenomena than our models allowed. That would be the comfortable answer. It would allow us to update our textbooks without upending our worldview. And maybe it's the right one. However, there is another possibility. One that is beginning to look less like wild speculation and more like a coherent framework that elegantly explains the entire vexing data set. This possibility is quietly changing the conversation in corridors and conferences where scientists dare to think the unthinkable. And to facilitate that conversation, to move it beyond binary shouting, a new tool has been quietly introduced. It's called the Loeb scale, and its very existence is a paradigm shift in miniature. You have probably never heard of the Loeb scale. It's not in textbooks, it's not taught in introductory astronomy courses. But it exists. It is being used in preprint papers, in closed-door conference sessions, and in the planning documents for future observation campaigns. It represents a fundamental, pragmatic shift in how we approach the most charged question in observational astronomy: is this object technological? The Loeb scale is a classification system for assessing the likelihood that an observed astronomical phenomenon is artificial rather than natural. Modelled after other useful scales like the Torino scale for asteroid impact hazard or the Rio scale for Yeti detection, it's a tool for quantifying uncertainty, for moving from binary yes-no thinking to graduated, probabilistic assessment. And 3i Atlas is the first major object to be publicly and seriously evaluated using this nascent framework. Here's how it works. The scale runs from 0 to 10. A rating of 0 means definitely natural with no plausible alternative. A 10 means definitely technological with the same certainty. The vast, overwhelming majority of objects sit at 0 or 1. Rocks, asteroids, comets, all the normal stuff that fits neatly into established categories. Moving up the scale requires ticking specific, evidence-based criteria that collectively shift the probability away from natural explanations. These criteria include non-gravitational acceleration inconsistent with known outgassing or radiation pressure models, geometric relationships suggesting navigation or control, compositional anomalies inconsistent with natural formation environments, apparent attitude control over extended periods, correlations between multiple independent anomalies, and the overall statistical implausibility of the observed behavior pattern when all factors are considered together. Based on the published analyses and the debates swirling in the community, 3i Atlas currently sits somewhere in the 3 to 5 range on the Loeb scale, depending on which research you weight more heavily and how conservatively you interpret the error bars. Let's be perfectly clear. A 3 to 5 is not confirmation. It's not even strong suspicion. But it is categorically not dismissal. It is a formal scientific acknowledgement that the object's behaviour warrants serious consideration, that the technological hypothesis cannot be ruled out based on current evidence, and that further observation, potentially including dedicated mission-level observation, is scientifically justified. It moves the question from the fringe to the ledger of legitimate scientific puzzles. The Loeb scale exists because binary thinking fails catastrophically at the edges of knowledge. Either it's natural or it's artificial is a useless framework when dealing with ambiguous, complex data. What you need is gradation, a way to say this is unusual enough to demand attention and specific tests without having to shout aliens. The Loeb scale provides that gradation. But more importantly, it provides legitimacy. For decades, suggesting an astronomical object might be technological was professional suicide. You did not propose artificial origins unless you had overwhelming, incontrovertible proof, and even then, you'd be treated with deep suspicion. The stigma was so potent that it prevented honest assessment of genuine anomalies. The Loeb scale changes that dynamic. It makes it methodologically acceptable to discuss technological possibilities as part of the normal scientific process of hypothesis generation and testing. It destigmatizes the conversation. That is why its quiet adoption represents a paradigm shift, even if the public hasn't noticed. Consider the historical parallels. The theory of continental drift was stigmatized for half a century. Alfred Wegener proposed it in 1912. The evidence was compelling, coastlines that fit together, matching fossil records across oceans. But geologists rejected it because they couldn't conceive of a mechanism. They lacked the concept of plate tectonics. So, they dismissed the observations rather than accept a theory that seemed impossible. It took until the 1960s for the paradigm to shift. 50 years of evidence accumulation were needed before the community was ready. After the shift, everyone looked back at Wegener's maps and wondered how it wasn't obvious all along. The Loeb scale is an attempt to prevent that kind of 50-year lag by giving scientists a neutral, quantitative tool to explore technological hypotheses before the evidence becomes so overwhelming that denial is impossible. Meteorites suffered the same fate. The idea that rocks could fall from the sky was dismissed as peasant superstition. Learned academics in the 18th century confidently declared stones could not fall from heaven because there were no stones in heaven. Eyewitness accounts were explained away as lightning striking the ground or mass hysteria. It took multiple well-documented witnessed falls and the careful work of skeptical scientists like Jean-Baptiste Biot to finally establish the extraterrestrial origin of meteorites. The pattern is immutable. Observations that don't fit the existing framework are dismissed, ridiculed, or ignored. The proponents of the new idea are marginalized. Then, slowly and reluctantly, the evidence piles up until it can no longer be denied, and the paradigm crashes. In the aftermath, everyone agrees the evidence was clear in retrospect. We might be in that pre-shift moment right now. The observations are on the table, the anomalies are documented in reputable journals, the statistical improbabilities are being calculated. But the broader community isn't yet ready to accept the implications, because doing so would require a seismic update to our fundamental assumptions about life, intelligence, and our place in the cosmos. The Loeb scale gives us a language for navigating this uncertainty without requiring premature commitment. A scientist can now say, this object is a Loeb 4, and their colleagues understand what that means, unusual, worthy of targeted investigation, not conclusive. It's a framework for discussion that doesn't force a binary choice, and its mere existence changes the conversation by making the technological hypothesis a legitimate category of scientific inquiry rather than a fringe topic for late-night TV. But tools only matter if they lead to action. If 3i Atlas rates a 4 or 5, what does further study look like? What specific observations would move it to a 6, or down to a 2, likely natural? What would constitute a smoking gun? These are the questions now driving the planning for the post-flyby phase. And as we ask these questions, one of the most logical and least dramatized hypotheses about what 3i Atlas has been doing comes into focus. Because if this is reconnaissance, you don't stop to chat. You scan, you record, and you transmit. And that mission profile makes more sense than any other. There's a common misconception about flybys. We tend to think of them as fleeting moments, missed opportunities, near misses where two ships pass in the night. This is a romantic but fundamentally wrong view. In mission design, a flyby is not a limitation. It is often the optimal observation geometry. You get close enough for high-resolution data, but you're moving fast enough that you don't get captured by gravity, you don't have to spend enormous energy on orbital insertion, and you preserve the option to continue on to other targets. Every major deep space probe humanity has ever launched has relied on flyby geometry. Voyager's Grand Tour was a masterpiece of sequential flybys. New Horizons flew past Pluto at 14 kilometers per second, fast enough that it couldn't stop, but slow enough to capture breathtaking images and data. That wasn't an accident of planning, it was the plan. Flybys maximize the scientific return per unit of mission complexity and energy cost. Now, extend that logic to interstellar reconnaissance. If you are surveying an inhabited system, a high-speed flyby has another strategic advantage. It minimizes your profile and reduces risk. You don't enter orbit, which would be obvious, sustained, and potentially threatening. You don't linger. You simply pass through the system's habitable zone, collect your data at the moment of closest approach, and continue outward. From the perspective of the resident civilization, you are a transient curiosity, a blip on the telescopes, a temporary anomaly to be debated, not a permanent presence to be feared. It is the ultimate low-commitment, high-yield observation strategy. 3i Atlas's closest approach to Earth brought it within about 140 million kilometers. In astronomical terms, that's close. Well within the range where high-resolution spectroscopy can dissect our atmosphere, detect the spectral signatures of industrial pollutants like nitrogen oxides or synthetic gases, map the pattern of artificial night-side lights, and capture the broad spectrum of our electromagnetic leakage. From AM radio to radar to television broadcast remnants sailing into space, you do not need to be in low Earth orbit or even lunar orbit to gather transformative intelligence about a technological civilization. You just need to be close enough that your sensors have sufficient resolution and signal-to-noise ratio. A close flyby provides that. What would such a scan prioritize? Atmospheric composition is a top-tier target. An atmosphere rich in free oxygen alongside methane, or laced with synthetic chlorofluorocarbons or industrial smog, is a screaming techno-biosignature. Radio emissions paint a precise picture of communication technology levels and population density. The spectrum of night-side lights reveals urbanization patterns and energy consumption. Infrared signatures betray waste heat from power generation and industry. All of this is detectable from tens of millions of kilometers away with sufficiently advanced passive sensors. You don't need to land. You don't need to sample. You just need a clear line of sight and enough integration time as you cruise past. Passive sensing is also strategically and stealthily optimal. Active sensing, like firing radar pulses at a planet or using laser ranging, means you are emitting energy. Those emissions can be detected, can reveal your presence and potentially your capabilities, and can mark you as an active prying entity. Passive sensing means you are a silent listener, a watcher in the dark, collecting the ambient light and radiation the civilization freely broadcasts into space. You give nothing away. If your goal is assessment without alteration, passive sensing during a fast flyby is the textbook approach. Now, the geometry gets even more interesting. 3i Atlas's closest approach to Earth coincided with a specific alignment between the object, Earth, and the Sun. This geometry isn't just important for illumination, it's critical for communication. If you are a probe trying to transmit the gigabytes of data you've just collected back to your point of origin, which could be light years away, You want the sun either directly behind you or positioned such that it doesn't create radio interference. You want a clear line of sight down a specific vector into the galaxy. There is a very speculative, carefully hedged debate among some analysts about whether 3i Atlas's post-perigee alignment might have provided an optimal transmission window along a specific celestial vector. If you draw a line from the object's position at perigee through Earth and extend it into deep space, where does it point? Some have noted, with extreme caution, that this rough direction bears a resemblance to the origin of the famous WOW. Signal, the powerful, unexplained narrowband radio burst detected in 1977 from the direction of Sagittarius. Let me be explicit, this is highly speculative, based on rough directional calculations and a historical signal whose exact coordinates are imprecise. It is not evidence, it is a moment. One more curious item that in isolation means nothing, but in the context of the stack adds a faint texture. What is more concrete is the nature of the flyby itself, perigee without interaction. 3i Atlas came close, maintained its sunlock keeping its instruments, presumably optimally oriented, collected whatever data it was designed to collect, if it is a technological object, and then continued on its way. No response to our radar pings if any were sent, no obvious transmission we could detect, no course change in response to us, just mutual, silent observation and departure. That is what reconnaissance looks like. You don't knock, you don't announce, you observe, you record, and you report. And if you are reporting across light years, you need powerful communications. How long would that take? With our own technology, transmitting data from the edge of the solar system is a trickle. Voyager's signal from beyond Pluto is a faint whisper of 160 bits per second, powered by a 23-watt transmitter. Scaling that to interstellar distances would require either vastly more power, incredibly focused transmission beams, or technology we don't yet possess. But if you've mastered interstellar travel, you've likely mastered interstellar communication. And you're not sending raw video. You're sending compressed summaries, spectroscopic fingerprints, analysed signal profiles, statistical assessments of technological activity. High-value information distilled into a manageable data package that could be transmitted in a focused burst during an optimal communications window. Then, your work at the primary target done, you continue to the system's strategic hub, Jupiter. Because Earth might have been the intelligence prize, but Jupiter is the operational base. Jupiter is where the long-term mission might truly begin. But I'm getting ahead of the timeline. Tonight the focus was Earth. The close approach is happening, or has just happened. The scanning, if it occurred, is complete. And now, we begin our own analysis. We sift through the petabytes of telescope data, looking for any change in the object's behaviour during its encounter with our planet. Did its rotation shift? Did its spectrum alter? Did it do anything that looked like a focused transmission? While we do this, the wider universe continues to remind us, in a chorus of other mysteries, that our certainty is a fragile thing, because 3i Atlas does not exist in a vacuum. It is part of a larger, stranger pattern emerging across astronomy in recent years, a pattern of broken models and humbled predictions. And that pattern itself might be the most important context of all.